to find confidence intervals. Just picking one at random, I'm going to go through some of these questions. I hope you're all looking at question 3 and the salt one. Great. Right. So,
is this the last section?
No, well, this is section 11, estimating a single mean, right? I want to do some more of these single means, and then we'll go on to the last section, which is the difference between the two, right? So we've got a little bit, right? So in this case, each man in a random sample of 9 men between this age group were asked how many sit-ups they could do in a minute. I think I did that one. I remember that question. I remember the sit-up one. So
can we do number 8?
The first marriage, so I'm not doing that one again. Right, let's do 5. Volunteers who had developed a cold within the previous 24 hours were randomized to take either a zinc tablet or a placebo for every 2 or 3 hours until the cold symptoms were gone. And I'll write these numbers down to remind me what's going on here. So 25 took zinc, okay, so 25, and they took zinc. I'm just writing this down to remember. And then there's actually 2 different groups going on here. And the second group, there was 23 of those, and they took the placebo. Okay, got that. And the mean duration for a cold in the ones that took zinc was 4 days, and the standard deviation for them was 1.1 day. That's good. And for the other group, wow, it took them twice as long, 8.4 days to recover, and the standard deviation was 1.6. So we have got everything written down here. Question A asks us to calculate a confidence interval for the people who took zinc. So I'm going to hit use salt. Hey, it's went in the right place for a change. I'll bring that over. Can you see the salt thing? And we are pretty much ready to do a confidence interval, aren't we? The sample mean for them was 4 days. The standard deviation for them was 1.1. And the number that was in that group was 25. We're doing a confidence interval and a 95%, and I'll generate the results. And these are the only 2 numbers that really matter for that question. So for the people taking zinc, the 95% confidence interval was roughly, let's do it to 2 decimal places, 3.54 to 4.45. Okay, that's written down. And now we'll do it for the other group, the ones that got the placebo. So in the placebo, it took on average 8.4 days to recover. The standard deviation was 1.6, and there were 23 people in that sample. And generate the results. And for the placebo group, the 95% confidence interval was from here to here. So that's going to be 7.71 days to 9.09 days. And that is that bit done. And I'm going to look at this data and do a little compare and contrast. That would be one of the things I would expect to do. If you look at the 2 confidence intervals, the first thing that I would notice, so hopefully you would notice as well, aren't these intervals totally separate from each other? There is no overlap. If I did a little number line, try and visualize it. There's 1, there's 2, there's 3, 4, 5, 6, 7, 8, 9. If you took the placebo somewhere about here and finishing somewhere about here. Sorry, if you took the zinc, right? And if you took the placebo, it would start about here and it would finish about here. Would you agree that there's evidence to show that taking zinc reduces your cold? You're watching this, Maggie? Take zinc, right? So zinc, placebo. I think that's pretty clear. Would you agree? Now, if there was an overlap, like the zinc was here and the green stuff, and the green was a little bit to the right and the zinc was a little bit to the left. So can you imagine, without any numbers, that one of them looked like this, right? And the other one looked like that. That wouldn't count as evidence. And the reason why that isn't evidence, right, that this takes longer and that's shorter, is because couldn't the answer in the red one be here and the green one be there? Couldn't it actually be the exact opposite in some circumstances? Here, no matter what number you pick, it's always going to be less days than this one. Here, some numbers, essentially in this range here, couldn't you get a green one that was smaller or bigger than the red one, in which case zinc doesn't actually help at all. In fact, it might make your cold last longer, right? That could be the truth. Are we good with that question? So you can use this to compare and contrast. If I was describing the zinc, wouldn't I probably advertise it as something like, do you want your cold to last half as long? Take zinc. Would you agree it's about half as long? Right? Your cold will be 5 days at most, compared to it could be as much as 10 days, right? You could phrase it all sorts of ways to get people to buy your zinc. And that was the end of that one. Now, the next one is question 6. There's not many of them, but they're kind of long. Is this one here, right? So, the latest antidepressant produced is currently involved in a testing process. 8 subjects, tiny sample. Nobody in their right mind would publish this when they're finished. And really all this is doing is a quick, yeah, let's see if it might work, right? That's the best you can say. Would you agree, doing anything with 8 people, you should be very wary of making big, bold conclusions about anything. But anyway, to continue. So 8 people tried it out, and the mean number of days taken before side effects disappeared. So they're really just looking at how many days, sometimes if you take an antidepressant, you can't sleep well, or you don't eat as well as you want, or you maybe get a headache, or you feel nausea, whatever, right? That's what they're talking about here. And we are going to answer some questions that you can see here. Now, the data is the raw data. Now, one of them I'm going to tell you right away. There's 1, 2, 3, 4, 5, 6, 7, 8 numbers, right? 8 numbers. The degrees of freedom, I did mention it yesterday, but I just did it passing, so I didn't push it much. If there's 8 numbers in your data, how many degrees of freedom does your data have?
7.
Right. 1 less than your data, right? So if you have 40 numbers, degrees of freedom is 39, right? That's the rule. Right, now, they want a point estimate. Do you know that's a fancy name, and I wish they'd asked it, for the mean. And they want the standard deviation of the sample. Well, that one at least is what I would call it, right? And then you're going to do these 2 guys, right? So I'm going to hit the salt button. And I'm going to go and show you once it's decided to do its thing, right? Now, let's see what's in descriptive statistics. Okay, there's the mean, and there's the standard deviation. You agree? Now, I got that by looking up descriptive statistics, so let me pick the mean, copy and paste it. And standard deviation. Let me copy and paste it. And then look at what kind of accuracy they want. Did they mention it? Yeah, that'll work. Now, I need to find a 95% confidence interval. Which of those menus at the top is the confidence interval guy?
Inferential statistics.
Okay, one sample. Oh, and would you look at that? Haven't they transferred all the information so you don't need to type it in? That's nice of salt, isn't it? And confidence interval, I'm assuming it's in 95%. 8.8, 24.4. So I'm just going to copy those guys and paste them. 8.8. And the upper limit, I'm copying and pasting it as we speak. And they want the answer to 3 decimal places, so that's the guy. And they want this one to 3 decimal places, don't they? Which makes it that guy. Has anybody noticed if you put the answer without rounding it off, does WebAssign say you're wrong because you never rounded it off? Or is it kind of lax and just takes it even if you've done it to 6 and they wanted 3? What's your experience?
It tells you you're wrong.
So if it says 2, you better do 2, right? If it says 3, you better do 3, which is fine. Now we all know. But I can imagine that might get you if you don't bother reading it. But it's right. Salt told me that. Why are you telling me it's wrong? Right? It was rounding. Are we you comfortable with how we did that? Right. Now, let's do a couple more then. Public health and safety officials have classified a virus called the Zika virus, which I vaguely have heard of but forgotten about. And this particular virus is bad for women who are pregnant, because I think if I recollect right, if the mother, before she's had the baby, gets this virus, it affects the child, right? It can affect the child. How does it affect the child? Well, horrible things like the child could get aborted, right? The pregnancy doesn't last. I think it's actually not that. I think it has something to do with the development of the child. In other words, the child's mental development is not as further developed as it could be. I think that's what it does. Don't quote me in that because I'm going by memory and I'm not 100% certain, but I think that's what it is. And this particular one is in Brazil, so I'm assuming that's where it started. Since I've not heard about it, it's probably one of those viruses, that's been gone and went, right? They found a vaccine, they caught it off at the source, and it never went anywhere. So here's a study based in Rio de Janeiro, found that the virus was more active near a body of water that was found to be polluted. Okay, so this virus hangs around dirty water, right? So they kind of knew where it came from. So this story then goes on and studies 20 water samples and found the amount of chemical waste using this unit, right? And there is the standard deviation. So that's the mean, that's the standard deviation, and they said 20. Do you see the numbers we need are all here, right? So when I hit salt, it looks, well, actually, let me pause a minute because I need these numbers. And when I put my screen up, it'll disappear. So it's 122 was the mean. Standard deviation was 17.47. And the sample size is 20. Okay, I got them all now. So, right place. This time we have to type in the mean. And the standard deviation. And the sample size. And the standard deviation is 17.47 because I was reading the wrong place. And confidence interval, and I bet you it's 95% because they have no imagination. Aren't almost all questions 95%, right? So generate the results, and we got the lower limit on pollution, and we have the upper limit. So, and guess what? I was right. It was a 95% confidence interval. So the lower limit was that number, and the upper limit was that number. And 3 decimal places means that this guy becomes 824. And 3 decimal places means this guy becomes 176. Oh, our degree of freedom guy, who should be a lot easier now, right? There was 20 numbers. Degrees of freedom, what's the answer?
19.
19, right? Okay. And now we've got a couple of questions. What would happen to the margin of error? Remember, the margin of error is basically the mean, add something, take away something, right? So if you have an interval, isn't it from the start to the finish, isn't that about 2 margins of errors, right? One to the right, one to the left, right? So what would happen to the margin of error if you used a bigger sample? What would happen to it? Get bigger, get smaller, stay the same, nobody knows. What is it?
Decrease.
So the margin of error decreases, which is good, because isn't margin of error decreasing more accurate, right? You know where the answer is in a smaller place. Now, what would happen to the margin of error if the confidence level increased? So instead of doing a 95, I say do a 99, right? So what would happen to it? Get bigger? Get smaller?
Increase.
You are on top of it today, yes. Does that make sense? If that's 90, why am I doing that there? If that's 90, wouldn't you have to be a bit bigger if you want to be 99% sure? Right. And my hands are just representing the margin of error growing on both sides, right? I could have said interval size and it would be the same answers, wouldn't it? That is the last question. Okay. So far, so good. Last one coming up. Are you looking at question 8? I've lost the place now. I'm not sure what you're looking at. Do you see question 8 here, guys? Okay. Did you know that eggs are an excellent source of chlorine and selenium? Well, if you didn't know, now you do. I didn't know either. They're also a good source of protein, which I did know. Vitamin D, which I didn't. And I don't even know what vitamin B12 is. So I definitely didn't know a good source of that. And phosphorus and riboflavin. God, there are a lot of stuff in eggs, isn't there? My first reaction is, do I really want phosphorus? But I think it's probably something your body needs. So the answer is yes. Now, eggs also come in various sizes. right? So you can get large and extra large, right? And so a nutritionist wants to quantify the nutritional value of large eggs. In other words, if you're going to eat eggs because they're good for you, and small eggs have got more good stuff in them than big eggs, then wouldn't you tell people, eat small eggs, even if it means eat 2 of them instead of 1 big egg, right? You're going to get more vitamins and all that good stuff. But the person needs to know the average weight of large eggs in order to accurately report the nutritional value. Well, me personally, I think I could tell the difference between a small egg and a large egg, but evidently this person wants to be nitpicky, right? So they'll probably have a number, right? Like if it's heavier than 10 grams, it's a big egg, right? And if it's less than 10 grams, it's a small one, right? Because, you know, eggs don't come in standard sizes. Okay, right. Here are all the sizes of these eggs. And so here are 10 eggs. The data are consistent with the summary quantities in the page evaluating egg quality traits of chickens. Okay, this is where the story came from. I've evidently somebody collected that data. So I'm going to use salt. Oh, come on. I got a stupid window. It's not going away. Come on. There you go. Here we are. Here is all the numbers. Now, what is it they want? Calculate the point estimate. So I need the mean. So if I go to descriptive statistics, actually, I've just figured something out. If I go here, don't they tell me the numbers? So I can save 1 line. So if I go to inferential statistics, there's the mean. I'm going to do the 95% confidence interval in a second once I find my window. Here. Confidence interval 95% generate results. Now, the lower limit is this number, about 52 and a bit grams. The upper limit is this one. So let's copy and paste and put here the smallest number. Put here the biggest number. And round them off to 3 decimal places.
The margin of error is just 1 divided by the square root of the number.
And that would be the conservative margin of error, but not this time. They don't want the conservative margin of error. What you said would be exactly correct, right? It would be 1 over the square root of 10 in this case, right? This one's a little bit sneakier. So I'm going to write that interval down, and then I'm going to show you how you get the margin of error based on these numbers. And you don't get it through salt, which is why I'm doing what I'm doing. So I'm going to show how you get it with not salt. The mean of this guy is 53.033. And if you imagine that's where the mean is. You've got a guy over here, which is him. And then you've got another guy over here, which is him. Now the distance from the middle to the outside, that's this one, is called the margin of error. And the distance from here to here is also called the margin of error, because don't we take X bar and we add and subtract the margin of error to get the error interval? Does that make sense? Now, won't the distance from here to here then be 2 margin of errors? 1 margin, 2 margins. Won't that distance be 2 margins of errors? Does that make sense? Now, If you want to find what one margin of error is, shouldn't you just take the distance between the start and the finish, which is 53.240, take away 52.826 and half it. That's how you got it. So just find the total distance from the start to the finish and half it. And that's how you get all margin of errors, right? The distance from the start to the finish, right? Big take away small divided by 2. So on my calculator, here it goes. Put a little bracket. 53.240 take away 52.826 all divided by 2. And I screwed up there. Let's find out what I did wrong. There we go. I didn't do a bracket at the start. I hit something else. And the margin of error is 0.207. And we're done.
Mr. Robinson, can't you also find it by doing the last half of the confidence interval equation, like the 1.96 times the standard error?
Do you know that 1.96 that you're talking about? That would only be for a normal distribution. That number changes when it's a d-distribution, which is why I couldn't do it that way. But I just thought of another way. Couldn't I take this and subtract the mean from it? Couldn't I just find the distance from here to here? So that would be this number, right? Take away that number. And that would get me it as well. Since we're on different ways to do it, couldn't I take the mean to this number and subtract them? And wouldn't that also be the margin of error? Or the one I did do, the difference between these two halved, which is also the margin of error.
Okay, so mine is 0.205. And
Okay.
how come it says on number C, it says suppose the nutritionalist cut the MOE in half, what sample size should be used? And it says,
oh, that's a new question, right? The question I've just answered is the second part of A.
yeah, I was just wanting to see.
Right, so now we got these last three questions that he is talking about, which are C, D, and E. And the first one was, suppose that the nutritionist would like to cut the margin in error of in half, right? Can you imagine them wanting to do that? So you want the margin of error to be half what it was. Now, right now, the sample size that we have was 10 eggs, right? And we want to know what kind of sample, right? How many, what sample size we should use to make that happen. Right, I'm going over here and just changing some things so we can check our answers. Now, if you want to have a sample size that is half, you would probably think, unfortunately it's wrongly, that all you need to do is double your sample, right? Instead of having 10, have twice as many, right? Now, the reason why that doesn't work is on the bottom, don't you have a square root of n? Now, if you had a square root of 10, and then you did a square root of 20, that guy and that guy are not double. Don't you need a 40 there to double the thing up? Now you say, well, how does that work? Well, square root of 40 is 4 times 10, which is 2 root 10. So do you see, if you want to take a square root of 10 and make something, you know, half the size, don't you have to use 4 times your data? So the correct answer to question C is use a sample size of 40. Now question D, oh, by the way, if you want to treble it, right? See if you want to make something 1/3 the size, 9 times the data. See if you want to make the margin of error 1/10 of what it was. You don't use 10 times the numbers, you use 10 squared. You use 100 times the number. Right? If you want it a half, you don't 2 it, you 2 squared it, right? You multiply the sample by 4. 1/3 by 9, 1/5, 25, right? And so on and so on. Now, which of the following combinations of confidence levels and sample sizes will produce the smallest margin of error? Right, I'll just show you the last 2 answers, then we can talk about why they are the answers that they are. Okay, oh, by the way, there's my 40. Can I make this bigger? Yay, good. Because this is quite small writing. Here. Which of the following combinations of confidence levels and sample sizes will produce the smallest margin of error? Don't worry about the mean and sigma unknown, those don't matter, right? So that's a confidence interval that you're using, and that is your sample size. Y is using a 90% and a 120 sample size. Why are those two together going to produce the smallest margin of error? Well, let's see what happens. Isn't a 95% going to be bigger than a 90%? Didn't we do that earlier, right? 90, let me go on my camera. There we go. That's 90. If you want to be 95, don't you have to make it bigger? Right. Now, if you do a sample of 20 or you do a sample of 120, won't 120 do a better job? And so that's going to be narrower. So when you put those together, that's why it's that one. Now, which of the following combinations of population standard deviation and sample size will produce the smallest margin of error? So the first number is the standard deviation, and the second number is your sample size, right? And again, you want the smallest margin of error, right? Well, isn't 120 better than 20? So you agree it's either this answer or that answer. Wouldn't a small standard deviation make a small margin of error, and a big standard deviation make a bigger one? And that's the answer to why it's that one. And that is the end of that section. Are we good? Any questions before we move on? Okay, so the next section that we're going to deal with is estimating the difference between two means. So it's going to be chapter 11 again. I'm not on the right page, am I? So it's going to be Math 146, chapter 11. And here we're going to estimate the difference in two means. So we know how to find the estimate for a single mean, but how do we kind of upgrade that to the estimate the difference between two different population means? So this is the kind of, you have two different groups, right? So let's do a little bit of theory before we get too caught up. Typically in these stories, you're going to have two populations. So population one, I'll go back to doing my usual American thing, is Scotland. And the second population here is going to be, say, America. And we are interested in seeing, is there any real difference between these two groups, right? And so we take a sample of the first population, which is 100 Scottish, and maybe the second sample, the Americans, maybe it's 150. And we find out the mean of each. And the mean of this group, let's say, what are we measuring this time? The number of hours that they spend watching television in a day. And Scottish people, it's 4 hours, and Americans, it's 4.3 hours. And the standard deviation is 1.2, and for this one, it's 1.4, right? So if this data was correct, a typical Scots person would spend 4 hours a day watching TV with that kind of standard deviation. And the average amount for an American was 4.3 in that one. Now, superficially, would you say that there's some evidence that Americans watch television more than Scottish people? Not by a lot, but right, a little bit, right? 0.3 difference. Now, that might be statistically significant, or it might just be in the randomness of the sample, right? So our job is to try and figure out whether that's truly a difference that you can measure, or whether it's just randomness and there's nothing to see here. So we are going to look at that guy called the sampling distribution again. And the mean of the sampling distribution will be that guy. Right, so you just take the two and you subtract them. So in this case, it's going to be 4, take away 4.3. And in this case, that means it's going to be negative 0.3 hours. Are you comfortable about how you would find the mean of the sampling distribution? What that means is, suppose we did this, whatever this is, hundreds and hundreds and hundreds of times, right? And we subtracted one from the other, right? We took the first one, subtracted the second. Wouldn't we get an answer that would probably be round about there, give or take a little bit? And then you have, as you'd expect, a standard error. And they go and they call it various names. So I'm going to call it standard deviation. But if I sometimes call it standard error, well, you realize I'm essentially talking about the same thing, right? Because, you know, sometimes you'll do a question and they say standard error, and technically it might be a standard deviation, but it's the same calculation anyway. So why don't I put them together and tell you the calculation? Can you remember doing this with P1 take away P2? And it ended up being a bit of one guy plus a bit of the other guy. This is what it looks like in our situation. That's the formula. Now, if I cover this guy up and you simplify it, do you know that you just get S over the square root of N? And if I cover this up, don't you basically just get S over the square root of N? So that formula is not as weird as it looks, but it is the standard error.
I don't get it. What's above the S? Is that a 2? Is that S21 divided
It's
by
S1. I guess if I put brackets, it might help. It's
squared.
S1 squared and S2 squared. Right. So back to this story here. If I wanted to find the standard error of the difference between the two groups of people, it would be the square root of 1.2 squared over 100 plus 1.4 squared over 100 and 50. So if I calculate the standard error here, it's going to be this ugly fella. So the square root of 1.2 squared divided by 100 added 1.4 squared divided by 150. And the answer I get here is 0.17. Okay, I rounded it off to 2 decimal places. Now the sampling distribution has this shape to it. So this is what would happen if you took lots and lots of samples. Right in the middle, you get this guy, negative 0.3. And then you go 1, 2, 3 standard errors this way, 1, 2, 3 standard that way. Now, since the standard error is 0.17, don't I just add 0.17, add 0.17, and add 0.17? So I'm going to do that in the calculator. Negative 0.3, add 0.17, gives me negative 0.13. Then you get positive 0.04, and then finally positive 0.21. Now, if you go the other way, you're going to get negative 0.47. If you do it again, you get negative 0.64. And if you do it one more time, you get negative 0.81. Are you comfortable about how I built this table? There's the mean, 1, 2, 3 going this way, 1, 2, 3 going that way. Now, this particular diagram lends itself to using the empirical rule. So suppose I wanted to use this diagram and I wanted to find a 95% confidence interval for the difference between, the two groups. How many standard deviations either side of the mean should I use to get a 95% confidence interval?
Two.
2. So we would take this guy, negative 0.3, and technically you would add and subtract 2 standard errors, right? Well, I've already done it. I mean, isn't it that number and that number? So that means that our 95% confidence interval for the difference in hours watched by Scots compared to the Americans is somewhere in the range negative 0.64 all the way up to positive 0.04. Right, so typically Scots people watch TV about 0.6 of an hour less than Americans, but it could be as much as, oh, actually don't Scottish people watch the TV more than Americans by 0.04. Since this interval contains 0, can I now say that there is no evidence to show there's a difference between the two? Because couldn't the answer have been positive 0.4? Scots people watch it more. Couldn't it be negative 0.4? Scotsmen watch it less. So if your interval contains 0, you can't say any significant difference between the two. Can we pretend in a different question it was negative 0.8 to negative 0.3? Can you imagine a different set of data? That's what I got, right? If you got that, wouldn't that be evidence that the first population smaller mean than the second, right? Because if they're all negative, doesn't that mean this guy take away that guy is negative, which means this guy has to be smaller, right? Small take away big gives you negative. So that would be the equivalent to saying Scots watch it less. On a different world, can you imagine it was 0.5 to 1.7? Now, do you notice this interval has nothing but positive numbers in it? Now, if the difference between this mean and that mean is positive, isn't the logical conclusion is that this has to be bigger than that? And so this would be evidence, actually, that the Scots watch it more than the Americans. So do you see how you can do the confidence interval to decide which one statistically is bigger or less than the other, or there's not enough evidence, which is actually the one we got. And that is perfect timing.